Our next speaker is Dr. Chris Field, who is a professor of interdisciplinary environmental studies and the director of the Woods Institute for Environment here at Stanford University. And he'll be speaking to us today about the breadth of connections between health and climate change. Thank you.
Thank you. And it's been a fabulous meeting so far, and I want to start out by emphasizing a comment that David made in the first session, which is that there are innumerable links between climate change and health. And one of the frustrating features of studying climate change is that every thread you pull on leads you to issues that not only impact health, but impact health through diverse pathways with multiple kinds of connections. And I want to illustrate that today with 4 little vignettes about relationships of the connection between climate change and especially heat that have really set me back on my heels as a climate change guy. And they have surprising and important dimensions that just illustrate the richness and complexity of the topic, but also many of the opportunities we have for developing solutions. So the 4 issues that I want to talk about are changes in wildfire. I've heard a lot about wildfire smoke and the fact that following decades of improvement in air quality around the US especially, we've seen degradation in recent years as a result of wildfire. New research on the global burden of mortality from heat that really resets the way we think about the relationship between temperature and mortality, especially across areas of different income, and has been the central factor in the economists resetting the social cost of carbon from a number around $50 to close to $200 per ton of CO2. I'm going to talk a little bit about this idea that we might be moving toward conditions of unsurvivable temperature, wet bulb temperatures warmer than about 35 C, where a healthy human can't survive unprotected for more than an hour or so. And then I also want to have one vignette that speaks to the issues of compound issues, particularly new evidence about the consequences of combined heat waves and power failures. So here's the global pattern of the trend in wildfires over the last 20 years. And I think most people would have expected that we would have seen a dramatic increase. In fact, there's been a dramatic decrease, almost 20% decrease in the annual area burned in wildfires between 2000 and 2020. This is almost entirely a result of decreased savanna burning in Africa. Africa is gigantic. On this scale, where we're seeing a decrease from 4,500 to about 3,600, the largest wildfire year we've ever had in California is 16. So just to put things in context, the amount of land that's consumed in wildfires in Africa is truly vast. Here's the pattern for a bunch of regions around the world with the global pattern in the upper left. And you can see that there are some areas that have seen consistent increases in area burn and wildfire over the last 20 years. That's certainly been the case in the coastal regions of North America, where by most measures we've seen about a 5-fold increase in wildfire. Eastern Siberian forests have also seen an increase. But in other areas that have been impacted profoundly by wildfires, for example, in Southeast Australia, there's hard to say there's a trend. There certainly was one catastrophic year, but whether or not there's been a trend is far from clear. And I think what this points out is that with almost everything that's a climate change response, there's a tremendous amount of texture spatially and temporally. And in some places where you have profound trends, there are other places where we at least haven't seen evidence to date. If we look at this in terms of the drivers for wildfire, this is a plot of the fire weather severity length, the raw numbers at the top, the change in number of days in the middle panel, and the fractional change, the percent change in the length of the fire weather season in the bottom panel. The middle one is probably the easiest to understand. What you can see is that there have been profound increases in the length of the fire season in Western North America, in Eastern South America, in much of Southern Europe, moving across the plains of Asia, and in Eastern Australia. Fire weather season length is probably the strongest control on the risk of wildfire, especially in Western North America, where the recent wet year we've had really illustrates the fact that if the snowpack lasts until the middle of the summer season, and the time that's available for wildfire risk and ignition risk goes down and down and down. But in Western North America, we've seen a really profound increase in the fire weather, in the increase in fire weather. This is September, October, November fire weather index. And what you can see is that that's increased dramatically. And you can also see in the right-hand panel that there's really clear evidence that when the fire weather index is less than 5.5, that substantially less area is burned than when the fire weather index is more than about 5.5. So it's really clear that there is a climate change and fire area link that jumps out most clearly in this relationship between the vapor pressure deficit, the ability of the atmosphere to withdraw moisture from the vegetation, and that's profoundly sensitive in an exponential way to the air temperature. And what you can see is that over the historical period, a very, very strong relationship between the seasonally integrated vapor pressure deficit and the area lost in wildfires. The lead author on this study, Park Williams at UCLA, argues that this relationship is so strong that it doesn't really allow any room for other factors to have a dominant control on this probabilistic interpretation of the area consumed in California wildfires. This study would imply that essentially 100% of the signal in the increase in wildfires is due to climate changes that have already occurred. Another study that Williams led said that there is an additional influence that's due to historical fuel management and fuel accumulation, and that we might be looking at somewhere between 50% and 100% of the trend being due to climate. But overall, a really strong signal in the Western US, and a signal that goes exactly the opposite direction if you look at the global scale, because of the profound decrease in savanna burning in Africa, where most of those fires are human set, and changes in basically farmer behavior have resulted in the profound decrease in fires worldwide. I want to switch now to the global burden of mortality, and new analysis led by the Climate Impacts Lab. This paper is led by Tama Carlson, was published in the end of 2022, shows really clearly that if you look at excess mortalities, they tend to rise once the average annual temperature gets much above about 25 C. And you see that whether you're looking at rich countries across the top row or poor countries across the bottom row, and you see it whether you're looking in regions that are already cold on the left-hand column or regions that are already hot on the right-hand column. The implication of this for mortality going forward, really striking. And this is end of century estimates for the high emission scenario, RCP 8.5, that you've already heard about. And the implication is really profound. So blue areas have a decrease in heat-related mortality. Red areas have an increase in heat-related mortality. And the implication is that essentially in the rich world, we see decreased mortality as a result of warmer average temperatures. And in the poor world, we see an increase in mortality. And you can see the pattern for Oslo, Chicago, and Sao Paulo, all of which are seeing actually a decrease in heat-related mortality across the spectrum from cold to warm. But in Beijing, Delhi, and Sydney, representative of warmer conditions, you can see a substantial increase in mortality, with the biggest effects being across sub-Saharan Africa and South Asia. If we look at the implications of this for the overall burden of mortality, what you can see is that the climate effects shown in the two left-hand bars on this figure are comparable to the effects of other major diseases like heart disease and infectious diseases and injury. The colored bars in the middle show the contrast, the stark and frustrating contrast between the very large impact increasing the burden of mortality in low-income areas to being a benefit in high-income areas, and showing that the effect is really profound in the warmest areas in the red bar, and much less in the areas that are already cold. One thing we should probably think about a little bit is this contrast between RCP 4.5, a high emissions scenario, and RCP 8.5, which is a catastrophically high one. And until recently, we had thought about RCP 8.5 as kind of business as usual, but we actually have made a remarkable amount of progress on where we're headed over the coming decades towards end of century. And RCP 8.5 is an incredible, valuable indicator of where we would go if we were in a world of continuing high emissions. But I think we've already turned a corner and are headed for end of century conditions that are more RCP 4.5 like, even without additional policy work. RCP 4.5 is warming between 2.5 and 3 by the end of century. Totally unacceptable level of warming and an incredible motivator for additional action. But we actually have moved importantly away from the catastrophically high RCP 8.5, and that's good news. The next vignette I want to talk about is this increasing recognition of the risk that we could be looking at a future world in which conditions are so hot that humans can't survive unprotected for more than a few minutes. But we understand a lot about the climate physics that can produce these conditions, and they're rare, they're really unheard of so far, because when you have a really hot, wet atmosphere, you can think about it as it's almost like throwing gasoline on a fire, that the air really wants to rise. As it rises, the water wants to condense, and that makes it rise more. And it's really hard to have hot, humid conditions that are so hot that that we pass this dew point threshold of about 35 C. But we can have conditions that tend to get us very close to that and could surpass it in the future. And the mechanism by which that happens is if there's a zone of high pressure, it's called blocking there on the figure, it produces air that's basically falling out of the upper atmosphere. That air, as it's warmed by compression, tends to be quite dry, but there are some places in the world where especially the transport of moisture from nearby coastal areas can lead to conditions where you get this potentially lethal combination of very hot temperatures and very moist air. And if you look at the historical pattern of where we've seen daily maximum wet bulb temperatures that approach this limit of lethality It's the red points on the figure. And there are a few near the Yucatan Peninsula. There are quite a lot in the Yemen, Iraq, Saudi Arabia area. And then there are a few across the northern tier of Pakistan and India. And these are the areas that are real concern for the potential of surpassing this threshold of survivability. And here's a way to think about this. In the left-hand figure, you can see a plot of how much additional warming do we need on top of the warming that's already occurred to push us to this 35-degree wet bulb. And you can see that especially in the Persian Gulf, that there are already many regions where additional warming of on the order of 2°C would produce these lethal wet bulb temperatures. And if you look at the area that would be impacted by these, in the right-hand figure, you can see that the area on land stays pretty close to zero. We still have some margin of safety until a warming occurs that's between 2.5 and 3. And at least for me, that's one of the clearest thresholds that we can't pass in future warming, really the threshold where we transition to unsurvivable conditions. Okay, the final vignette that I want to talk about is the compound effect of power failure and a heat wave. And power failures are incredibly common. We had a power failure at my house last night. I couldn't believe it. The middle of the summer, no wind, but PG&E left me without power for the whole evening. And I actually was going to add a couple more slides, but I couldn't because power failure. Anyhow, this is the number of major power failures in the U.S. over the last several years. It's been increasing rapidly. And just a few weeks ago, there was a really nice paper saying, what are the implications for premature deaths and for emergency room visits in a situation where there's coupled heat and power failure? And they did this analysis for Atlanta, Phoenix, and Detroit with several different scenarios. The left-hand panel is excess mortalities, and the right one is emergency room visits. The core experiment, the power on, power off, is the leftmost series of bars. And what you can see is that especially for Phoenix, which is already really hot, there's a gigantic increase in both mortality and emergency room visits as a result of having a 5-day heat wave where you also have a power failure for the first 2 days and only gradually restore power. And you can see, especially for the emergency room visits, there's also a very big increase in the power off setting in the Atlanta case. And I think that that's very much our future, is a situation in which we're dealing with compound events. Chris Ebi already talked about the options we have for moderating heat waves in the absence of air conditioning. And it's important to think about because in many cases, we are very likely to see these compound disasters that do things like knock us out of the ability to have it, the normal safety features in the system. The street trees, cool roofs, mid-century and late century are other scenarios that these investigators ran to say, well, are there other things we could do to moderate the effects of the power cutoff? And the answer was, in general, not. You still get a big increase in mortality and a big increase in emergency room visits when the power goes off. So let me close with just a couple of thoughts. So the surprises to me is that fire is huge, but it's globally far from uniform. And we actually have seen this global decrease in area burned. The link between heat and excess mortality is profoundly important, and it's especially pernicious because of this effect of hitting the poor world the hardest and the hot world the hardest. We've talked a lot about the emergence of lethal heat, and it's a real risk in localized areas, but we still have some margin before we reach the threshold at which unsurvivable conditions are likely to occur. And then finally, I just want to close with the thought that when we think about the world of the future, we really need to be thinking about intersections between multiple changes, and this example of heat waves and power failures is just one of the many things we ought to consider. Thanks so much.